Hi, welcome to lab number 6, which incorporates checkoff number 1 of the major project. In checkoff number 1, we calculate all of the remaining R and C values for the major project. We enter them into the healthy parameter file as a script, save it and publish it, and then we start writing some of the lines needed for the main program. At the end of this video, I will give you some help on doing problem number 3 on this week's homework. Well, let's start with this checklist, which is found in the major project in the appendix of the textbook, which lists all of the items that need to be completed to complete checkoff number 1 of the major project. Starting first with good notebook practices. Well, we aren't keeping a notebook this year, so I'll assume that if you have turned in your worksheets on time and in good order, that we have completed that task. Filled in table C2 with units. We did that table and turned that in last week's lab, so that has been completed. Filled in table C4 of those 5 approximations. We also did that in last week's lab. We don't need to turn that in again, and we can consider that to be completed. Going on for this week, we need to finish up the calculations of all the remaining fluid R and C values. We did 2 of those last week. We need to finish those out, and we need to put them in a summary table. Now, where are we going to do those calculations? On the first 2 worksheets of this week's lab. On the first worksheet, I'll have you do the calculations of the remaining 4 resistances, and we'll have you use the equations that we developed on worksheet number 1 from last week's lab here. I hope you saved that. And you'll also need to refer to several figures from the textbook. We'll use the units that we decided upon, millimeters of mercury, liters, and liters per second for each of those values. And you'll need to refer to such items in the appendix, such as the Wiggers diagram, which is in the appendix, the pressure loop, which is found in the appendix, and table C3 that is found in the appendix. You also may find that reviewing the video from last week's lab will help you to see how to calculate the R's and the C's. Now, as you calculate each resistance here, when you get the final value, please circle that value and put units by it. You might as well include the R that we found last week on this sheet also for completeness. Now, why do we ask you to put them all on this sheet here? If we find in checkoff number 2 in a couple of weeks that one of your values is way out of line, we can come back to this sheet and figure out how to correct that. For the compliances, you will calculate the remaining 5 compliances on this sheet here, again following the equations that we developed last week on worksheet number 1 here. And once again, you may want to review the video from last week's lab to help you to determine those values. As you get each compliance, circle the final value and put units also on this sheet. Now, where are we going to store in the summary table all of the values that we just calculated? I'll show you that next. We're going to enter in the R and C values onto the 3rd worksheet of today's lab. But before we do, I'd like you to decide how many significant figures you're going to report your values in. I know it's going to be more than 1, because I know we can estimate those values better than 50%. You choose how many significant figures you're going to report your values in, put that number here, and then justify that choice with a sentence in this region right here. Going on, we're going to put the R and C values into this box, which will form the lines which we will enter in as a script into MATLAB in a minute or 2 that will become the parameter file for the healthy parameters, starting first with the 5 values of resistances. Here are 2 of my values. Your values are going to be a little different than mine because everybody reads those graphs a little differently than anybody else in the class, but they'll be in the same ballpark. And as long as they're in the same ballpark within better than a factor of 2 or so, they should all work. If you write big, you might want to take that entry and put it on the same line as the previous entry. Just separate them with semicolons to save some space. MATLAB will allow you to do that in the script just as well. Now you don't want to put any units here because MATLAB will not accept units as an input. So what you'll do if you want to have a record of those units is put them in a comment over here to the right. I'll leave that up to you whether you want to do that or not. Going on to the compliances, I've shown two of my compliances here. Yours will be a little bit different than mine, but if they're in the same ballpark, they should work. Once again, if you wanted to save some space, you could put two entries on the same line separated with a semicolon. Notice that there are a lot of zeros behind that decimal point. So when you type this into MATLAB, be careful that you keep the right amount of zeros there. It's easy to drop a 0 or 2 as you type it into MATLAB. So be careful with that. If you'd like to put this into scientific notation, this number here would be 7.0 e minus 4. You could do that, put everything in scientific notation if you would like. You should have all 6 of your compliances in this region here. Going on, the main program is going to need to know the residual volume in each of the 5 compartments of the cardiovascular system in order to calculate pressure from volume. We will enter in those 5 residual volumes here. You've seen these residual volumes before when you did some calculations, but let me remind you that they come from this table here, in this column here. If that compartment happens to have some lumped parts of it, add those parts together to get the total residual volume in that compartment. Do that for those 2 compartments. Oh, and also, let's enter in the residual volume of the heart as a separate entry to make the 5 residual volumes here. My residual volume for the aorta has a 0 behind it to represent residual volume to follow the textbook. It's been pointed out that that 0 sometimes can be confused with that O for aorta. So if you'd like to change the subscript you use to represent residual from a 0 over to something other than a 0, such as maybe an R, you could use a different subscript if you'd like. Just be consistent throughout the entire program with that. Going on, we're going to have to enter in the 5 initial values for each of the 5 compartments. That is our best estimate of what the initial volume starts out with in those 5 compartments. It will get readjusted during each cardiac cycle slightly, but we need to start it out with some volume. Those initial volumes will come from this table again, from this column right here. Add up these values to get volumes for each of the compartments and enter those in as liters in this region right here. Notice that that subscript is not an I, it's a 1, because this represents the very first time step of the 800 time steps that we're going to start out the volume at. Once again, it'll get readjusted slightly during a cardiac cycle. Each of these volumes needs to add together to get a total volume of all of these to be 4.2 liters. That's the amount of blood that a normal human has in the systemic cardiovascular system if there has been no bleeding. So make sure those add up to 4.2 liters. Going on, we'll enter in the time constants for the exponential rise and fall of CH, the compliance in the heart, both during systole of 30 milliseconds and diastole of 60 milliseconds. These values come from a Johns Hopkins study that I will talk about in next week's lab. There's no tau in the keyboard, so we're going to let that be represented by capital T sub S for systole and capital T sub D for the time constant for diastole. These are time constants of exponential rise and fall. These are not the duration of the systolic time or the diastolic time. These are exponential time constants, different than the duration of each of those segments of cardiac cycle. And then we need to generate a time vector t. And I've used 800 time steps, each one a millisecond long, to be 800 milliseconds long. The time vector will start at 0, increment by a millisecond, and then end at 799 milliseconds. Now, why does it end at 799? Because if you start at 0, when you add that together, that makes a total of 800 time steps. I've used the colon operator to generate that here. If you'd like to use linspace, it'll accomplish the same thing. I'll leave that up to you. Now, once you've entered all those lines by hand in the box, you should type them in as a script in MATLAB, save that file as your healthy parameter file with some titles such as healthy with your initials here, and then publish that as a PDF M file for Checkov. You know how to publish because you've done that before for some homework. And turn that PDF file in with the 4 worksheets to check out for today's lab. Now that we've done a calculation of all of our R and C values and have put them into a summary table in the parameter file, we can go on and put some vectorized equations into the main program to get it started. We will finish the main program next lab. So let's finish the lab this week by completing worksheet number 4, which is where we're going to write by hand some of the lines that will be in our main program that we will finish next week and get running next week. So this is the start of the main program. And this is my suggestion of how you arrange those lines. Starting first with the input command. This is where we enter in the parameter file, the various values of the parameter file for the situation that we are simulating with the main program. This is a very misunderstood input command because what's inside the parentheses is not the name of the parameter file, but rather this is just a prompt to remind you now is the time to type in on the keyboard the name of the parameter file. What's inside these single quotes is not executed by MATLAB. It is simply displayed because MATLAB stops at this point and waits for you to type in on the keyboard the name of the parameter file. This is simply a prompt to remind you to do that. And I'll let you decide what kind of prompt you want to put into the parentheses there. Then following that are 5 lines from homework set number 6, problem 3. That's due this Friday. It's part of your homework set this Friday. I will give you a lot of help at the end of this video on how to complete that problem, that homework problem. What it does is it generates the compliance in the heart at each time step I, going between systole and diastole, between these 2 limits with these 2 time constants. When you complete the homework set this week, you will take 5 lines out of that homework and put it in this location for your final program, for your final main program. Next comes the outer for loop, or the B for loop, where B increments up to 10 for 10 repetitive heartbeats. Inside of that outer for loop is the inner for loop, which increments over 800 milliseconds for 1 cardiac cycle, or 1 heartbeat. So I goes from 1 to 800 for 800 time steps. The first section that we encounter in that inner for loop is where we calculate pressures from compliance. And here is an example of one of the lines where we calculate the pressure in the heart based upon the volume in the heart at that particular time step and the compliance in the heart at that particular time step. There will be 5 of these lines. We wrote one of those lines, a sample of those lines in last week's lab, but you've also written a couple of those lines for your homework set last week, homework set 5, problem 2, which we call the mini major project. You'll need 5 lines here. To get those subscripts and to keep those subscripts straight, I would suggest that you look back at this schematic and you just go around the various segments of that schematic and use the subscripts that are appropriate for that segment, for that particular segment of the cardiovascular circuit, to write these 5 lines here. Next comes Poiseuille's law, where we find the flows generated by pressures and resistances. And there are more than 5 lines here, because for 2 of those flows, namely Q1 and Q9, there is a valve in the way. And so for those lines, you're going to have something that I have suggested here, that we say that if the pressure in the heart on the inlet side of the valve is greater than the pressure on the outlet side of the valve for that particular time step, then the valve is open and the flow follows the normal Poiseuille's law here. Otherwise, the valve is closed and the flow is zero. Notice that this end statement, which is needed to match up with that if statement, is not off to the left here, like it often is. Rather, for compactness, I put it right here. Now, MATLAB will give you sort of a minor warning about that, but it is okay. It is fine to leave it there for compactness. And then you will have some flows that don't have valves in the way. We'll let you finish those out. And then a final one that does have a valve in the way, that's Q9, that will finish out this particular section here. Going on, we'll have 5 lines for 5 flows based upon conservation of volume. And based upon what you've done for your homework, you know how to finish out these 5 lines. And then we'll finish up with the segment that represents the update of each of the volumes using Euler's method here, 5 lines, where we get the next time step of the volume, say in the heart, is based upon the previous time step volume plus the flow that's going into the heart, in or out of the heart at that particular time. And there'll be 5 lines here, and I'll let you write those 5 lines in here by hand. And then we come to the end statement that ends the inner for loop. After we go 800 times around inside of this inner for loop, we've done 1 cardiac cycle, 800 milliseconds. We fall out of that inner for loop, and we're going to need to plot some things and to do some displays of different values. We will, next week, put some more lines at the bottom of the inner for loop before we come to the end of the outer for loop, which is right here, which completes the 10 cardiac cycles that we will display. So these are lines. You do not have to type these into MATLAB yet. We will type them in next week. But you should need to save this worksheet because we will add to it in next week's lab. Now, just to remind you that to check out for this week, you'll turn in the 4 completed worksheets along with the parameter file that we typed in just a minute ago, but you don't need to type the main program into MATLAB yet. And that will complete a preparation for next week's checkoff. Now let's turn our attention to problem number 3 on this week's homework assignment due Friday. Here is a help sheet that has been included with the worksheets for the lab this week. You don't need to turn this in. This help sheet is simply to help you to solve problem 3 in the homework problem due this week. And what that problem has to do with, it builds and generates a row vector 800 points long for the compliance in the heart during diastole and then systole and diastole, rising and falling exponentially, following the same timing as the Wiggers diagram, which has been so helpful to us in the past. Let me point out that every variable that has an exponential behavior follows this general expression during either the rise or the fall. And it says that the value at any time is equal to the initial value before it changes exponentially to its final value where it's heading towards. All of that times e to the minus t over tau, where t is time and tau is the time constant, plus its final value. Well, we're going to use that to generate the dropping of CH during systole and the rising of CH during diastole. So we'll first generate a temporary curve that represents the change in the compliance when it drops during systole using this general expression. Notice that the compliance in the heart during systole starts where it ended up at the end of the previous diastolic period. So the beginning value, the initial value, is CHD, and it's heading towards the final value, which is the limit CHS. So using that, we can write the fact that CH temp, which is going to be this curve right here temporarily, following the general expression up here at the top, is given by the initial value, which is CHD, minus the final value, which is CHS, times e to the minus t over the time constant, which we're calling T sub s, capital T sub s, plus CHS. And that gives us an expression that we can put into MATLAB that will generate this curve right here. Now, what do we do with that curve? We want to take this section right here and cut it out and paste it in right here into the final curve that we want of both diastole and systole put together following the timing of the Wiggers diagram. So how are we going to do that? Well, down here at the bottom is going to be the main program that you're going to write for this homework problem, and it's going to start out with the same command that we've talked about just a couple of minutes ago, input, and then it asks what file name. Here's where you're going to type the parameter file of this parameter file that you're going to put together. What's in the parameter file? It's going to be CHS to be this value and CHD to be that value. Those are not the values that you're going to use in your major project. These are simply values that for this particular case we're going to use for CHS and CHD for this particular case. Now, your values are going to be different for the major project. We're going to call the time increment 1 millisecond, 800 total milliseconds. Here are the time constants for systole and diastole, and these are the same for your major project. Everybody's going to use those. Here is the time vector that we generate with the colon command, or you could use linspace if you'd like to generate that same time vector. Now, going back to the main program, the very first thing you're going to write is what we've just written in above for generating CHS temporarily, which is CHD minus CHS, that's the initial value minus the final value, times e to the minus t over tau. But be careful in MATLAB, the way we enter in an exponential is not with an e, but with the EXP command. EXP stands for exponential, parentheses, minus t over tau sub s. And then we add the final value, C sub hs, to end that line. Notice that this is not an e by itself, because e by itself represents a power of 10. So if you want the exponential e, you're going to have to write out exp. Okay, now let's go back and figure out how we're going to cut out this curve that we've just generated with that line in MATLAB. Well, this is going to be a touch tricky because the time vector starts with 0 and ends at it ends at 799 out here. We only want the first 250 milliseconds starting from 0. But the index for MATLAB never starts at 0. It always starts with 1. So the index in the row vector that was just generated temporarily here starts at 1, not 0, and after 249 milliseconds, the index is actually 1 greater than that, 250. Write that in on your help sheet here. Just write that in. And then we go in over here, and we say we want that to be in the spot of the Wiggers diagram, this systolic drop right here. Now that goes in the Wiggers diagram between 100 milliseconds and 349 milliseconds for a total of 350 milliseconds. But the index, once again, is 1 more than the number of milliseconds. So the index, and you can write this in, starts at 1 here, and the end of that previous diastolic period goes from 1 to 100, and then the next systolic period starts with an index of 101. I'll state that once again. It starts with milliseconds of 100, but with an index of 101. So write that in. And that it ends with an index of 350. Not 349, but 350. And then to finish this out, we'll add 1 to each millisecond to get the index. The index is always 1 greater than the milliseconds. And the index, of course, ends at 800. Starts at 1 and ends at 800. So, if we want to take this portion of the temporary curve that we've just generated and cut it out and put it into the final curve that we want, we will go down to our main program, and at this line right here, this line right here, notice it says that for our final CH, not CH temp, but our final CH, from index 100 to 350, we want to take the piece of the original CH temporary that goes from 1 to 250, and we take that out and let that be the portion of the final CH from 101 to 350. And just point out once again, we're taking this section of the temporary curve from 1 to 250, and we're taking that out and we're sticking it in the final curve from 101 to 350. That's what this line right here does. That's called cut and paste. Now, I'm going to let you finish this out to do the homework in the following way. You need to now generate the temporary equation for CHD, for diastolic CHD temporary, and you're going to use this same general expression, except you're going to put in different values for the start value of CHD temp and the end value for CHD temp, and you'll put in its time constant. So you're going to write an equation there. You're going to put that in your main program for MATLAB right here, and then you're going to add an index 1 down here to each of the milliseconds. I'll let you fill that in. I haven't filled it in. You're going to fill that in. And then you're going to take this piece of the diastolic temporary curve, you're going to cut it out by its index numbers, and you're going to stick it right in there by these index numbers in the final CHD curve. And you're going to take this portion, the early portion of diastole, and stick it in there with these index numbers. Now, I know it's a little awkward to have the Wiggers diagram cut the diastolic period in two, but like we talked about before, that's so you can very clearly see what happens in the isovolumetric contraction of systole right there. We didn't want that to be stuck off to the far left axis. So you're going to finish the main program out by writing in the expression for CHD temp, and by cutting and pasting in these other two lines, and then you plot CH as a function of time right here. You label the x-axis and y-axis and put a title on and put grid on. And then one final note, on this plot you can change the color of the line and the line style, but this is a little different than anything we've done before. Do not put markers on this plot. You know, I've said you want to put markers on all experimental values, but these are not experimental values. These are calculated theoretical values, and they don't need markers. Besides, if you put markers there, it's going to blur out the line because there are going to be so many markers. So don't put markers in this plot. So write the main program, also enter a parameter file. I've given it to you right here. Run that, and that will be the solution for problem 3 on homework set number 6. When you complete this week's lab, you will have obtained the healthy parameter file for checkoff number 1 and be ready for next week's lab, where we're going to complete all of the lines for the main program, enter it into MATLAB, and get it running with the healthy parameter file. Now, there may be some debugging that you're going to have to do in order to do that next week, so I urge you to start early. If you run into any problems whatsoever, please get on the help link and ask for help. See you next week.